It's a real pleasure to be here this morning, and I must say I don't really understand this, okay? Here is a beautiful satellite picture. These are a dime a dozen. Satellite meteorology was invented on this campus. It's still the world headquarters for it. That's true. It's not well known, but it's true. So I've never really understood how can you not be interested in the weather. As a young boy growing up in southern New England, it's a snowy place, and my particular interest in the weather started at a very young age. I was delivering morning papers, and I was the first person to make footprints in the snow. And these first intellectual stirrings were exactly coincident with the moon landings. So there were many, many mornings where I imagined myself as Neil Armstrong making the first footprints on the moon. And that exact sort of magic and fable-like quality to the weather has not left me. So Jordan, I'm sorry, on a beautiful summer day we're going to talk a little bit about snow, because there's nothing that compels me more than the snow. Something about the slate gray and white mixed in. Here's a storm from our own city of Madison from a few years ago. Just stimulates my soul and my intellect at the same time. There's nothing else like it in the natural world, including, in fact, I'm saying this 2 days after the eclipse. Eclipse, who cares? I prefer a snowstorm any day of the week. They change everything. It's picturesque, it's paralyzing, and it's powerful. And there's just nothing you can say that's better than a snowstorm. Look at this. This is on University Ave. You can't even tell where you are. That's beautiful, isn't it? Now, as luck would have it, when I first arrived here on campus in 1994-95, in January 1995, we had a great snowstorm, 14 or so inches of snow right in my own backyard. It was just before the semester began, so there I am, free, nobody's knocking on my door. Myself and several interested graduate students were routinely going from the window watching something like this happening to our satellite observations, to our radar observations, to our numerical forecast models, and animating the output from those numerical forecast models. Now, before you laugh dismissively at the weather geeks that you've just conjured in your head, I want to show you a few of the things that we were privy to that day that are literally miracles of the second half of the 20th century. So here is a surface from our forecast model that day where the equivalent potential temperature is a constant. Now, the details of that doesn't really matter much. It's a variable that combines temperature and moisture to some degree. Now, what you can see, this is supposed to keep on going. See, it's just what we thought, Kerry, right? We tested it and it didn't work. It's supposed to keep on going. As it goes, there's a fold in this surface that develops over about Tulsa, Oklahoma, and then progresses northeastward toward Green Bay. It turns out, and anybody can see it. I'm sorry it's not animating continuously for you, but if you watch this, you can see it. Even if you've never seen such a surface before, you notice that fairly compelling fold. And that fold, its progression across the central U.S. is exactly coincident with the heaviest snow in the storm, which closed the University of Missouri in Columbia that day. 21 inches of snow. That's more than a seasonal total for them in one day. Now I can show you another perspective of this. This one is from an elevated northern perspective. See the little yellow ribbon? We're only going to see it once, unfortunately. That is an air possum. So it's like a balloon of air that's embedded in the model, and we can trace where it actually goes. I'm going to go back. I'm going to try a trick here. Do it again. And you can see that parcel of air starts. No, it doesn't work. Didn't work. Anyway, that parcel of air started in southern Alabama near the ground, moved toward the position of that fold, and then once it got there, it turned counterclockwise and rose, ascended. And the ascent is what produces clouds and precipitation in these storms. It turns out that right in that folded region is where constantly there's a production of upward vertical motion, and that's driving the precipitation. Why or how, we didn't know at the time we were watching it. So we were lucky that these tools, not only the numerical weather prediction model, but also the animation software, were built on this campus. So I have these tools at my disposal. I'll tell you, when I interviewed for this job, I thought, oh, I've got to get this job. Nobody has these tools except people at Wisconsin, and I really made hay on them for a number of years because they were unique. And so I had the opportunity to lead a research program over a number of years that really solved mysteries regarding the production and distribution of heavy snow in these winter storms. And that has a huge positive societal impact. It's a really good feeling to be able to involve in that. Now, if you're interested in the weather as I am, you know that individual winters might come along that are rather boring. One in particular that caught my attention some years ago, 2011, 2012. It was warm, drippy, no snow, just terrible kind of winter for me. I'm sure you all loved it. I hated it. So I thought, how can I measure the intensity of the winter in a non-parochial way? I've got to break out of this view that the winter is only the winter where I live. So I thought about this for a while, and I thought, here's an idea. Why don't I take a measure of temperature in the lower troposphere, about 850 millibars. That's 1 mile above sea level, so it's close to the ground. Minus 5 degrees C, I can see how that's distributed around the northern hemisphere every day. In fact, I can look at it 4 times a day. And what if I calculate the areal extent of that cold air? And then just start to see what the numbers tell me. It'd be kind of interesting. So this turns out, I have 69 years worth of data that I can do this with. This turns out to be the biggest extent of the minus 5 air at a mile above the ground in the last 69 cold seasons in the northern hemisphere, January 21st, 1984. So what I can do is 4 times a day, 90 days in the winter, I don't count leap days, from December 1st to February 28th, I get 360 calculations of that area, average them all together, I get a seasonal average areal extent of the cold air in the lower troposphere. Watch what happens when you do that. Oh my God, I don't know what that line is, but anyway, the top line is the minus 5. See, this is the problem between Apple and PCs. We're talking about all this great research. That's a problem I'd like somebody to solve, right there. So the top line is the minus 5 degrees C a line. So every dot represents an average of 360 of those aerial calculations. And look at that. That trend is down. I put a black line in the trend line. It's systematically shrinking. We don't make as much cold air in the northern hemisphere over the course of the winter as we used to do in 1948-49. It's true at 4 other threshold temperatures. I used 3 different reanalysis data sets to do it. They're all created slightly differently. They all tell the same story. Incidentally, this slope, this rate of decrease is the same as the rate of decrease of the Arctic sea ice in February. Wow. Okay? You can't escape this. This is what people have been saying since 1998 global warming has stopped. Nonsense. Utter nonsense. Okay? Utter nonsense. Not only can you get seasonal averages, you can look at trends that go from year to year. So I'm looking at the daily average every day from the winter of 71, 72. The blue line is the average, and then it's straddled by plus and minus 1 standard deviation. Almost every day that winter had an aerial extent of this minus 5 air greater than the 69-year average. Almost every day. And it was particularly cold in early February. President Nixon was in China. I remember that, delivering papers, seeing the breath in his outside in Peking. Here last winter, not even the warmest winter ever. But again, against the same average and standard deviation. Very few days greater in aerial extent than the average. Almost every day less than that. Wow, that's pretty interesting. In fact, I can measure the departure. This doesn't work. I can measure the departure from average in terms of standard deviation. So we shared the exact same math word today, which is great. And when I do that, I can rank extremely cold days, which are days in which the aerial extent of the minus 5 air is 2 standard deviations bigger than the average for that calendar day, or extreme warm days, where it's 2 standard deviations smaller than the average for that day. And look what I get. It looks kind of front-loaded for the cold days. This is from 1940s all the way to the 2010s. And back-loaded with the warm days. And that impression is correct. There have been 117 extreme cold events, by this definition, in the time series. Not a single one since a week before I interviewed for this job, and I've been here a quarter of a century. We haven't had one since 1994. And there have been 237 such days on the warm side, 154 of them since 2000. Unbelievable, huh? So over the last 68 or 69 cold seasons, the aerial extent of the northern hemisphere cold pool has shrunk systematically at 4.5%. Sounds like nothing. In the atmosphere, you change the sea level pressure by 4.5%, you go from a day like this to the center of a Category 2 hurricane. So 4.5% change in the atmosphere is a big change. This shrinking is a result of greenhouse warming because everything else is the same. The sun's the same distance away from the Earth as it was. The Earth is tilted the same. The length of day is the same over the northern hemisphere in all those days. The only thing that's different is the radiative balance. And if you have increased greenhouse gas concentrations, you allow more radiation to be re-radiated to the surface and warm the planet. There's just no other way to argue for a reduction in the production of cold air during the winter. And extreme cold events have ceased. They don't occur anymore in the northern hemisphere. We haven't had one since February 13th, 1994. The score is 191 to nothing since that time, warm versus cold. Even our Badgers will not vanquish the most woeful opponent by that score this fall. So what can we do with this kind of research? There's maybe several different ideas. One that's kind of been rolling around in my head for a while is, can I tell when the winter is about to end? And I don't mean forecast it now, in late August. I mean while we're in midstream. So for instance, we're in the middle of January, or first week of January, in the middle of a cold spell. No one is going to expect that's the last time we're going to be visited by cold air. But somewhere in that cold season, so the odds there are 90 to 10 that you're going to have more cold air. Somewhere, though, there's a 50-50 day. And I think that 50-50 day changes every single year. It's not going to be the same. So what if I could tell, say, Land's End, this winter, we're in the middle of it, there's a 60% chance on February 25th that this is the end of the winter. Your outerwear sales will cease. You might want to rush to make the sale price drop way to the ground, get rid of your inventory costs before your competitors do, who weren't talking to me. And as a consequence, you save yourself some money. So I think we can probably do that. And here's the way we'll do it. Weather systems, remote sensing by satellites, big here at the University of Wisconsin, and climate system dynamics. I've been doing this for 20-something years. There's no place better positioned in the world to make this bridge between weather and climate than the University of Wisconsin-Madison. And I think that we can do that. And we would love to talk to you about what you see as your needs and your desires and what we can bring to the table and what we might be able to work on together. So that'd be really exciting for me. So thanks very much.
Thanks, Jonathan. We have time for about one question for Jonathan.
A lot of us use air travel for business and recreation. And I remember reading recently that as the atmosphere warms, the planes may not be able to get enough lift because of the temperature change. Is there anything you can tell us about that?
I don't think that'll be a systematic problem. Phoenix International has the longest runways in the world, I think, because they have the highest average summertime temperature of any airport. When it gets to be about over 120 Fahrenheit at Phoenix, they do not take off anymore because they can't generate enough lift. But that's a very specific, very unusual problem. They kind of built it into their cake, actually, a little bit with the long runways. I don't think that's going to be a systematic effect of global warming on air travel. There will probably be other ones, though, that are interesting. We could talk about that at lunch.